Hi there. So today we'll go over 8.2, Part 2. Example 3. A rectangular lot is separated by a fence. The large region has an area of 20 meters squared, greater than the smaller region. The total area of lot is 145 meters squared. Determine the area of each region. So what we have so far is a large region, that's 20 meters squared, greater than the smaller region. So we have two variables, and let's label them. So we can say L for large region and S for small region. And we know the total area is 145 meters squared. Let's start by stating our variables before we set two equations. So L stands for larger region, S for smaller region. So we know that the larger region is 20 meters squared greater, so we add to the smaller region. Okay, so this is our first equation. And this comes from, right here. 20 meters squared greater than the smaller region. So that's the first equation we can find. Second equation should be from our total area of lot right here. So we can denote T for total area. So let me just scroll down. So we know that T is total area of a lot, and we know total area is 145 meters squared. But we also know that total area is actually adding smaller region and the larger region. So we know that S plus L equals 145. Okay, so because we were given that the total area is 145, you just sub in. You sub in right here. So because our equation 1 had L on the left-hand side, I'm going to rewrite our second equation so we have L on the left-hand side by itself as well. So I'm going to take away S from both sides. So we have L equals negative S plus 145. Or we can say, I guess it really doesn't matter here, but 145 minus S. We now have two equations. And because we're trying to determine the area of each region, as in area of S, what S and L is. So what we can do, we can first draw or graph these two lines and look for the intersection that satisfies both equations. Okay, so I'm going to use color blue for the first equation, and let's graph it. For the increment, I set it up so it's going up by 25 for the horizontal axes. And I will set this as smaller region and larger region as a y-axis. It really doesn't matter which side you do, but I just chose it this way. And for the y-axis, go up by 20. All right, so once we're done, let's try plotting the points first. So I chose this, but unfortunately the numbers don't work out that nicely all the time, so we do have to write a table of value just to check where things go. Let's set S and L here. So the left column is always an independent variable, in this case S. So I'll go with 0, 25, 50, 75, and 100. And this kind of gives us enough information to draw a line. So if S is 0, then L equals 20. And it goes up by 20 every time. So, oh, not 20, but if you go 25, so 45 here, 70, it goes up by 25, so 95, and then 120. So let's graph it. So 0 and 20 is right here. 25 and 45, maybe here-ish. And 50, 70, in the middle here, 70, eh? So 75 and 95, close enough right here. Let's plot one more, 100 and 120. Ah, okay, there we go. All right, so let's connect the points. Okay, it looks good. So this is equation 1. Never mind the arrow here because it does have a upper bound. So it goes up to 200 and it'll stop. So I'm not going to draw that. So just don't draw the arrow there. Okay, so we're going to graph the second line here, equation 2 in red. Same idea, we're going to make a table of value for this, and S on the left hand side, L on the right hand side. So I'll choose this time, I'm not going to choose every single point. I'm going to start 0, 50, and 100. So when S is 100, you plug it into that second equation and you get 145. When S is 50, you get 95, and when S is 100, you get 45. So 0 and 145 is somewhere here. 50 and 95 is somewhere over here. And then 145 is around here. Let's connect the points. Okay, so I think this is pretty good, so we'll just keep it this way, equation 2. All right, so notice that we have an intersection here. The only problem is we don't know what that point is exactly. So what we can do, we can approximate it. So we approximate approximately, I'd say 60, 65. Let's do 65. 65. And then it's a little bit above 80, so let's do 82. Let's do 82, yeah. Approximately. Because we don't exactly know the value of it just yet. So this is when solving it graphically doesn't give you an exact value. So the only way we can double check is to solve it algebraically. So let's try completing the algebraic solutions here. So we first write down the two equations we set up. So first equation's L equals to 20 plus S, and equation 2 is L equals to 145 minus S. Okay, so how to solve it algebraically? You let L equal to L. And each L is referring to a different equation. So the first L from equation 1 is a left-hand side L. Second equation L is a right-hand side L. So essentially what we're doing, we're just subbing in. So yellow L is 20 plus S, and the pink L is 145 minus S. So we have an equation now with S on both sides. So when you're solving for a variable, you do have to isolate that variable on its own. So we first need to collect the like terms. So we're going to, I like to have a positive S, so I'll just add S to both sides first. So we should have 20 plus 2S equals to 145 plus 0, and I'm not going to write 0. And because I want to isolate S, we need to take away 20 to remove the left-hand side 20, and we're left with 2S equal to 125. We divide the coefficient in front of S, so we have S equals 125 divided by 2, which is 62.5. Okay, we have solved S. So let's sub this into equation 1 or 2 to solve for L. I chose equation 1 and sub it back into equation 1. So we have L equals to 20 plus S, and we now know what S is, so we sub in 62.5, and L equals to 82.5. Oops. Okay, so we found the area of smaller region and the larger region. And this time, you don't have to approximate it. So notice our approximation was 65 for the smaller region, but it was actually 62.5. And the larger region was 82, our approximated ones, but then actual was 82.5. What are the chances that we can guess the decimal places correctly, right? So this is why we should always verify using algebraic solution. For this question, we can state that in words, smaller region or area is 62.5 meters squared. Don't forget the unit. And the larger region is 82.5 meters squared. So we're done with example 3. Moving on to example 4. Peter and Nancy are writing a math workbook. Peter has already written 28 questions and can write 4 questions per hour. Nancy has already written 20 questions and can write 5 questions per hour. So we need to find, part A asks us, when will both writers have written the same number of questions? So they're looking for time. Part B is asking for how many questions will have been written in total at that time. All right, so we first need to understand what we are given. So we were given, I'll use pink for this one. What we were given is that these 28 questions, these were the initial number of questions Peter had. So we'll say initial number of Qs. Okay, and this one, he can write 4 questions per hour, and this is great. Same idea for the second line for Nancy. So 20 questions where she starts, so initial. And she can write 5 questions per hour, so this is rate. So I will set up the equation now. So essentially we're looking for how many questions will they have been written in total when the time arrives when they have the same number of questions. So we first need a variable. Let's name as Q as number of questions, because we're looking for how many questions there are, like same number of questions. So we need to know the number. So we're going to label that as Q. And T for time. So essentially how we can calculate Q, because time is always independent, right? So Q is always going to depend on the speed that Peter writes. So for example, this is going to be for Peter. So rate times time, okay? And then we're going to have to start with his 28 questions. So initial number of questions. Initial number of Qs right here. All right, so this ends up being Q equals to 4T plus 28. And this is an equation for Peter. Let's look at Nancy's case. So Nancy, we're going to use the same setup. So Q equals the rate that she can write is 5 questions per hour times T. She's starting at 20 questions. All right, so we have two equations. Same idea for example 4, we're going to graph these lines and then look for the intersection. So because time is always independent this time, we do have to label the horizontal axis as time t. And the number of questions would be on the vertical axis. So these are the increments. So time will increase by 1 hour each. 6, 7, 8. And then questions will increase by 10. 20, 30, and all the way up. All right, so let's start by making the table of value for Peter, because we don't have a nice number, because we have 28, so that's going to be kind of in between number every time we go up by 4. All right, so let's do T and Q. Let's try 0, 4, and 6. All right, so at 0, Q is 28. At T equals 4, we get 44. And when T equals 6, we get 52. Let's graph that line. So 0 and 28, somewhere here. 4 and 44, almost in the middle, but not yet, not quite. And then when T equals 6 is 52. When T equals 6, 52. Maybe I should have one more. Okay, we'll just leave it then and just connect the points for now. This is equation 1. And this time you could put an arrow there. Who knows how long he could write for. So equation 1 for Peter. For equation 2, I'll use red color. We do need a table of value here as well, but this is going to look better. So T and then Q. So let's do 0, 4, and 6 again. So 0 at time equals 0, we get 20 questions. At time equal to 4, we get 40. And then 6, 50 right here. All right, so let's graph it. 0, 20, 4, 40, and 6, 50 right here. Okay, so this doesn't look that nice. So let's try connecting it and then extend it as much as we can. Okay. This is a problem with graphing. Okay. Okay, well, this is my graphing skill, equation 2. So this is very unfortunate, but I can't seem to find an intersection here. Okay, so you know what? We'll drop it right here and conclude that it's somewhere here. It's somewhere here. I can't tell. It doesn't show in my graph. So either you have to draw a better graph, or you do have to solve it algebraically. So the copy of the filled in notes will have the approximation or maybe exact value, so you can double check. But during this lecture, I just can't seem to draw a straight line that intersects. So you know what? That's okay. We'll move on to algebraic solution here. All right, so let's look at part A. Well, actually, we'll do complete the algebraic solution first before part A and B because we can't seem to find it. All right, so we'll start by writing the equation 1 and 2. Equation 1 and 2. So first equation was q equals to 4t plus 28 and q equals 5t plus 20. All right, so we're gonna follow the same step as previous one. Let q equal to q. This q is this q, and this q is with this q. So 4t plus 28 equals 5t plus 20. So we're going to isolate t, or collect t first, and then you isolate the rest. So I'm going to minus 4t, because I know if I minus 4t, we're still going to have a positive t on one side. So we're left with 28 on the left-hand side, and 1t plus 20. Take away 20. We have t equals 8. We're going to use this to sub into equation 1. Q equals 4t plus 28. So Q, actually, 4 times 8 plus 28, which is 32 plus 28 equals 60. So Q equals 60. Okay, let's just double check our graph again. T equals 8. Okay. Maybe if I shift my blue graph a bit. Okay. All right, so our intersection should have been right here. Okay, but then again, we weren't able to approximate it because on our graph, we just couldn't see the intersection. But here we can confirm there should have been an intersection. Okay, so we can actually go back to part A and B and state your solution. So at t equals 8, both writers have written the same amount of questions, same number of questions. Okay, and part B, how many questions will have been written in total? So the total will be the writers each wrote 60 questions. So example 4 showed us how important it is to double check the solution algebraically to confirm. to verify. Okay, so that's it for today. I'll see you guys in the next video.